All right, so what I would like to do here, we're going to review, but some of it may not be. So let's talk about attributes of functions. So if we take and this is just right on your paper here, if we look at a function, what are some attributes? So what are some things, some qualities of the function that we can describe mathematically? What do you think? Say it again?
Just slope.
Okay, so we could talk about parts of the function that are increasing or decreasing, which would have to do with the slope, right? So give me an example. Where is an interval on this graph where the function is decreasing? Tell me a part of the domain where the function is decreasing. And by the way, when we talk about increasing, decreasing, a real common mistake that people make is you could probably say that increasing, decreasing, you could technically, well, you couldn't technically. You might mistakenly think that any part of this graph could be considered decreasing. Like this part right here, for example, that I'm looking at. If I were to walk from right to left, wouldn't that be decreasing? Okay, does that seem right though? No, so in what direction do we always assume that the ant is walking?
Left to right.
Left to right, and along the positive axis. So Tyler, what do you think?
X is greater than or equal to 2 or less than or equal to 4.
Okay, so in the interval between 2 and 4, the function is decreasing, isn't it? Okay. Now, if we want to be really technical here, so the suggested interval is greater than or equal to 2 and less than or equal to 4. Is the function decreasing at 2? Is it decreasing at 4? That's kind of weird. And this is a little bit above the scope maybe of Algebra 2, but we're going to talk about this in more detail in calculus, so it's kind of interesting. Yeah, you can't really say it's decreasing there, because what does it mean to be decreasing? Okay, it means that you're moving down with each step, right? But you have to be able to measure where you are relative to the previous step and the following step then, don't you? See what I'm saying? Okay, and so when you're at a place like there or right there, you're neither decreasing nor increasing, right? That make sense? Okay. And by the same token, I won't even bother asking you. You could all answer this. We would, for example, be increasing on the interval between 8 and 10, right? Would be an increasing interval. Good. Okay, what are some other attributes? Some ways you could describe a function. What's different, for example, about the point at x equals 4.5 and the point where x equals 5.5? Let me blow this thing up a little bit. It's kind of hard to see. So what's different about, say, that point and that point? Is there an attribute that's of the graph that's different? What do you think, Kristen?
One, the y value is positive, and one, the y value is negative.
Okay, good. So one, the function has a positive value, and the other one, the function has a negative value. That's important. Okay. So what about the transition between positive and negative? I can see a few of those up there, right? What about those? What do we call those? Zeros. Yeah, those are the zeros of the function, right? Those are frequently really important, okay? Important places on the function. So those are some attributes of the function. What else? Some other places that are, for reasons that we probably haven't really talked about a lot, or you haven't talked about a lot in math, but we spend a pretty significant part of the year, probably a good month or month and a half in calculus just searching for these kinds of places.
Maxima and minimums.
Yeah, maxima and minima. Singular would be a maximum, plural would be maxima, but those are important places, right? There, and there, those are maxima, and those are minima, right? And I guess technically that's a minimum too, okay? Although it's a different kind, but we'll talk more about that in future through here. Yeah, those are important places. We spend a lot of time in calculus just looking for, in calculus, we're gonna call those relative extrema. And might even in here this year a little bit. Those are important places. A lot of times when we're using a mathematical model and we're trying to analyze the model to like maximize profit or something along those lines, those are the kinds of places we look for in calculus. So there's lots of attributes of the function that are important. What if we want to calculate, so the word rate, what does that mean to you? Talk about a rate of change. That's something that we've talked about. It's a word we've attached to it. You already brought up this attribute. What attribute does that go with? Sam?
Slope.
Slope, yeah. So slope is a rate, right? Slope is a rate of change of the function. If we were to like calculate the slope of, let's say, that segment right there, what's the definition of slope? Rise over run, correct? So m equals rise over run. Well, the rise is, in this case, the rise is the change in what variable? Y. Okay, so then you've also talked about that as being change in y over change in x. Okay, so that's a rate, right? That's the rate of change of the function, right? Because isn't y just the same as f of x? So if you wanted to, you could even think about that as being the change in the function over the change in x, right? Same thing. So a rate of change is a slope. What is the slope on this interval right here? Yeah, we could make a little slope triangle and find out, right? If we draw a slope triangle, we see that delta y is 1, 2, 3, 4. Oh, no, it's not. It's 2, isn't it? Because the scale's a little tweaked, right? And then, looks like that's 2. Is it 1? No, it's 2. Yeah, because you see the scale's a little different. It's been stretched vertically a little bit. So the slope is 1 there, even though it doesn't look like it because it's been distorted a little bit. What about if I wanted to do something like, let's say, calculate the average rate of change from there to there? How would I do that? What do you think? Now let's talk about that for a second, an average rate of change. A good model for maybe exploring rate of change would be speed in your car, right? Because speed is just the rate of change of distance, right? So let's say we're going to take a trip to Hermiston. If you look at the speedometer, you're going to be seeing the rate of change, instantaneous rate of change is what we call it in physics. It's the rate of change at that moment, right? Let's say that we were to calculate for when we're going by the route elevator, let's say that we're going to calculate, we're going to do a little experiment, and we're going to drive for 1 mile, and we're going to time how long it takes to go that 1 mile, and it takes exactly 60 seconds. So what's our rate of change by over that 1 mile section of road? Let's say the cruise control is on. 60 miles an hour work out to be, right? Okay, does that mean that our speed is 60 the whole time? No. What if I were to calculate the time it took me to get to Hermiston, and let's say it took me, for whatever reason, maybe there was some construction or something, let's say it took me an hour to get to Hermiston, and let's say it's 30 miles away. What's my average rate of change then? Okay, 30 miles an hour, but does that mean that I'm going 30 miles an hour very often? No, not necessarily, right? An average is sort of a smeared out value over the entire trip. Make sense? Okay, it's descriptive of a longer interval. So how am I going to calculate an average rate of change between those 2 points? What do you think?
Oh, maybe 10 by 3.
What do you think? Take this one and multiply by 3 because it's 3 times further away. That would mean the slope would be 3. That's pretty steep.
Never mind.
Well, it's an idea. That's fine. What do you think?
Just make a big triangle.
Let's make a big slope triangle. Okay, let's do that. Okay, so there's our big slope triangle over the whole interval, right? From orange to orange. Let's see, the rise is still 2, but this time the run is 10, I think. So what's my average rate of change then? So the red slope is, 2 over 10 reduces to 1/5. Okay. Now, let's just assume this is a car or something. Is the slope of the function or the speed of the car ever actually 1/5? No. It's not, is it? Right? It's always either looks like +1 or -1, right? Make sense? It's never actually 1/5, but that's descriptive of the whole trip. That's a useful number for us, because if we wanted to calculate, if we wanted to estimate how long is it going to take to go further with that pattern, right? Well, that's probably a number that might be useful to us, right? What about this one? What if we wanted to go from green over to green? Without even really having to do much, you could probably tell me that the average rate of change between those two values of x is what?
0.
Yeah, we said that. 0. Everybody see that? Right? How do you know that right away?
Slope 0.
Yeah, there's no rise. Yeah, it's a horizontal segment, isn't it? Right? Okay, makes sense? All right. Okay. So, how could you describe, so we talked a little bit about maxima and minima. Let's say you wanted to describe to somebody, what are the characteristics of a maximum? So how do you describe, what are the conditions that have to be there for us to have a maximum? And by conditions, I guess what I'm saying is, relative to its surroundings, what do you know? Joe? Oh, so it's high on the function, that's true. Or higher than maybe its surroundings. What else? Kirk, any ideas? How do I know, how do I create a maximum?
It goes up and comes back down.
Yeah, exactly. So it's a transition from an increasing slope to a decreasing slope, right? By contrast, a minimum is a transition from decreasing to increasing. Seems pretty simple, but that becomes important later in math. All right, so let's look at some some stuff here. Okay. Oh, there we go. Okay, look at this second discussion point right here. If a function is increasing on an interval, what can you say about its average rate of change on the interval? Now, that's not to say that it's increasing at the same rate, right? But if it's increasing on an interval, what do you know is definitely going to be true about its average rate of change? It's going to be positive, yeah. Okay. Let's look at this example here. So the graph is already sketched, but just ignore the graph for a second, because this is one of the things that you're going to be asked to do. We're going to do some modeling with functions, and this is really important. This is kind of a weird approach in a way, but I like it. This book does things that's a little different from what I'm used to. But mathematical modeling, that's really probably arguably the thing that most of you will do the most with math. If you happen to go on and become a mathematician, well, maybe it won't be. Or if you become a physicist or an engineer. But if you go into any other kind of I would say any other kind of science, social science or science where math is sort of more of a tool than the emphasis, you're gonna end up using modeling probably more than anything else. And that's arguably the most important function in everyday life that math serves. Math allows us to create predictive models where we can, like for example, you wanna know what the weather's gonna be. How does the weatherman know? Well, they don't always know, but how do they make a fairly accurate prediction about what the weather, you're gonna be able to go voting this weekend? That's what I'm thinking about. Well, you know because it's a mathematical model. A bunch of data points are input into a model, then that model has been built on past experience and observations and data, and that projects what the weather's gonna be like in your region, right? How do you know which stock you should invest in? Well, if you're investing through, let's say a mutual fund, well, the people that run that mutual fund, that's what they do. I mean, they're just trained to develop a model that's gonna make hopefully accurate predictions about how fast certain stocks or certain commodities are gonna grow, how stable they're gonna be. So this is something we do an awful lot. Physics is essentially just one big collection of mathematical models, right? There's these math equations that make predictions about the way the world works. Okay, so let's look at this one. Lyme disease is a bacterial infection transmitted to humans by ticks. When an infective tick bites a human, the probability of transmission is a function of time since the tick attached itself to the skin. Okay, during the first 24 hours, the probability is 0%. During the next 3 24-hour periods, the rate of change in the probability is always positive, but it is much greater for the middle period than the other 2 periods. Okay? So after 96 hours, the probability is almost 100%. So sketch a graph of the function for the probability of transmission. Okay, so now they didn't give us much information there, but does it make sense that this is the kind of graph that based on that information we could all draw? I mean, it might look slightly different, but they're gonna look fairly similar, aren't they? So why? Let's talk about why does this graph fit? I'm gonna start calling on people, but you could avoid that by just raising your hand. Just tell me something about that graph that fits the description we were just given. How about the first segment? What do you think?
Yeah, first segment, second segment.
Yeah, look at the first segment. For the first 24 hours, there's no probability. For some reason, it takes longer than that for the disease to take hold. So there you go, right there's the first segment. What do you think, Matthew?
The middle segment has a higher rate of change.
Yeah, good, okay. So the steepest rate of change, the place where the probability is growing the fastest is that middle segment as it was described, right? There are, what else? How many positive, fairly steep positive segments are there? Like 1, 2, 3, right? It talked about how during the next 3 24-hour periods, the rate of change in probability is always positive, right? So positive, 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 but it's much steeper in the middle one, right? And then maybe the last one here. What about the end of the graph? It's almost 100%, right? So as you get out there to, 96 hours, the probability is almost 100%, right? Okay, makes sense? So could we do better than that? Maybe. How might we do better than that? What do you think? Well, what's kind of funny about that graph that maybe isn't completely realistic or accurate? What do you think, Kristen?
120 hours is at 100%, but it doesn't ever say.
Okay, so they kind of extrapolated there. Good. Okay, good. Anything else about that seemed just a little bit hokey? I mean, it's a better model than nothing, but are there some parts about that you think just probably it's not that way? Lyme disease is just a little microorganism, right? I think that microorganism is smart enough to know that at 47.99 hours, its probability of taking hold is increasing at a certain rate, and then a second later it automatically just jumps up. I think it probably works that way. What do you think if we wanted to find a more accurate graph we probably would want to do to this? You You think it's really a bunch of line segments connected? So if I wanted to improve on this, what could I do to draw this graph probably more accurately? Okay, so Emma's she's making the universal sign for smooth the curve out, right? So we could do this. We could go maybe something like that maybe. Okay, but the question is, we could all do that, but we're all gonna get maybe very different answers, right? Okay. Assuming though, let's just make the assumption that these points right here, we could say we could all agree on those points. Wouldn't it be cool if there was a way that we could take those points and say, okay, well let's all come up with a uniform, smoothed out model? That'd be great, wouldn't it? Well, there is. There is such a thing. It's called regression. It's a statistical tool. And I'm not going to spend time right now talking about what the regression formulas are, their statistical measures, and we haven't really talked enough about statistics for it to be very meaningful, but I don't think it makes any difference. Your calculator does it for you. Okay, we're going to go through an example of that in just a little bit. And we'll all get exactly the same answer. We put in the same data points. It'll give us literally what's called the best fit curve. Okay, so that's an extremely powerful tool to have. All right, so let's move on here. Okay, real quick, just try this one. If you want to work with your neighbor, that's fine. Try coming up with a curve. And we're not going to, obviously, we haven't learned about regression yet, so you're going to be maybe looking at linear models, so line segments. Graphic call. Dead batteries?
Sorry?
That's, oh, you're fine. Once again, that's not a bad model, but let's learn about how maybe we could do this a little better. Let's talk about some ways that we could use some regression. And the kind of regression we're going to talk about today is just going to be linear regression. A lot of times, once again, linear regression, linear we know means line, right? So we're going to try to find the best fit line. This is something we try to do a lot. There's a whole process in physics and calculus that you'll learn about in a couple of years. Keep telling me what you're going to learn. About, kind of a linear modeling over very short intervals that's really makes calculations really easy to do. So we do stuff like this a lot in the future. So let's take this here. What are we trying to find here? Photographer hiked through the Grand Canyon. Each day she stored photos on a memory card for her digital camera. When she returned from the trip, she deleted some photos from each memory card, saving only the best. The table shows the number of photos she kept from all those stored on each memory card. So we're going to use our graphing calculators to create a scatter plot first of all, and then we're going to use that data to create a linear regressional model. Okay, so how do we do this? Here's how you do it. So I guess we want to have this on the board. I don't need to put this up here. You've got this in front of you. This is the data we want to use. All right, so on our calculators, I'm going to pull up my calculator here, my fancy new calculator. Oh, this looks different.
It looks like Al.
Ooh, man. What's that?
It looks like Al.
Yeah.
We still got one from like 1980 or something.
Oh my dinosaur code. Yeah, I'm gonna start using that.
You know,
And
you s-
Judy
use the
Jeffkins
Roberts
last
class.
Yeah, it started beeping and Alex broke it.
Okay, so
Like what?
Remember that when you broke my calculator?
Eighth
Class,
grade.
It started beeping.
Eighth grade kept beeping and it's hard. You started playing the games on it.
okay, so we want to try to make a prediction about the number of photos kept based on the number of photos taken, right? She, for example, on one day she took 117 photos but only kept 25, right? We want to be able to have a linear model that's going to make a prediction based on the number of photos taken. What would you predict the number of photos she will keep will be, right? That's our model, all right? So to get that, we're going to go to Stat. We're going to go to Stat Edit. Okay, so when you go to Stat, you're going to see this menu on your calculator.
Stat button.
Right, stat button is kind of right in the middle top.
Oh, wait,
Okay.
is it?
I have a
Yeah.
Casio. Yeah, I got it.
Why don't you come up and grab one of these?
Then what do we do after stat?
What's that?
So I was gonna read 2 minutes.
2 minutes?
Yeah.
Yeah.
Well, why are they making our classes so short? Don't we get to just go as long as we want to?
No.
What's the deal with that? Okay, so we'll do this on Monday. That's fine.
We don't have school Monday.
You know, you guys have worked pretty hard. Take Monday off. We'll just go Tuesday, I think, next week. I'm just gonna go ahead and bring the calculators back up if you have one of mine, please.